Morning to everyone. That was Buddy Holly. And Chris, what cut were we listening to?
It is so easy.
It is so easy. We wish it were, right?
Yes.
It would be nice. Okay, there was a wrinkle that I didn't address adequately, I've been told, in terms of the problems that you had to do. And I'm just going to look at a number on the board, and what we are going to ask, what are the divisors of the number? Not what the prime factoring is, but just what are the divisors we could have? They are factors technically, but let's try it. We aren't talking about primes now, so the idea is how could I write a number as a product of two numbers? That's what it really amounts to. So if I look at 60 as I go to the board, and I have a 6-0, then I could write that as a product in a number of ways. Obviously, 1 and 60. And then I could say 2 and 30. Now I'm just getting the divisors, if you will, in a way. That 2 times 30, or I could do 3 times 20, correct? Or I could do 4 times 15. Or we'll get there. How about 5 times 12 first? Otherwise, I'm trying to keep some order as I'm going down. And then, yes, the 6 times 10. And then as I keep coming down, if you think of it for a moment, the next number that would divide is my 12, right? So if you think of it in this sense, think of the square root of 60. Okay, it has to be under 8, because 8 times 8 is 64. So if 7 won't go, then my divisors, in essence, are 1, 2, 3, 4, 5, and 6, 10, 12, 15, 20, 30, and 60. Those are all the divisors of the number. In essence, you're just going through the natural numbers all the way down, and I would say to the square root of the number. And you estimate the square root. That's probably the most methodical way of doing it. Now, if you want to have the divisors using primes to look at all possible divisors, then you could say that this is going to be 2 times 2, okay, because we're going to have, in terms of what I'm doing here, the 4 times 15, so the 3 times 5. And then if I look at those numbers, I could go ahead and I can just take them in pairs, any way they want, okay? I could take these in pairs any way I want. So for example, I could take these two together. I could take these two together in the outer one, so I could do something like this. Or I could do, and that certainly gives me a 4, it gives me a 15, I have a 6, I have a 10, and then what could I do? Well, I could take 3 of them together now. So I could say these 3 together, and that's your 12 times your 5, or I could take these 3 together, and that's your 30. Now, and so I could get all these out of this process. But what I didn't show you well enough was that process that was used in the book. And I hadn't anticipated that and just didn't. I was thinking of just going from here, and clearly I omitted something I shouldn't have. Let me come back to center, Chris. So what I'm going to do is come back to that process that's illustrated for you. And this is on page 198. And so the way this problem is stated is to list all the factors of 24. Okay, so we have all the factors of 24. And if I'm going to do that, you can see pretty much what I've done on the board is matching this. The natural numbers, 1, 2, 3, and 4. You skip the 5. But if you look at 24, what is the square root of 24? Under 5. Not half, the square root. So if I think of 5 squared as 25, it's going to have to be smaller than 5. If I said 6 squared, I'd be at 36. That'd be much too large. So my square root's between 4 and 5. So I take the natural numbers up to the square root. Then I try each one. And what this gives me now is a list of what? All the divisors that I could have. And the little strategy that's stated over here in the little box, if you want to get all the factors, or all the divisors, once you've come down this list to your 4, and then if you went further, you would repeat, correct? So you only go up to the square root, so you come down here and then pick up all the others. So we have 1, 2, 3, 4, 5, 6, 7, 8 divisors. Now, the only reason for doing that, in my view, is to avoid primes. Now, if I look at a problem given in the text where you were working with, okay, I've got to find the problem. It is a problem in which I believe you're doing a double list, trying to find the GCF out of a list, and that's a technique that is used. And I thought, yes. Okay, it's 199. So if you wanted to find the GCF of these two numbers, you simply run the list. Okay, let's come off there for just a moment. I have no idea why I am trying to get a better white balance and not doing all that good. See if I can. Okay, let's try that again. A little bit better. But what I'm noting, I run the factors, the divisors, if you will, of 24. And I run the divisors of 60. And then I just hunt for what? The largest common factor. Does that remind you of something?
Yeah.
Common multiple? When we were hunting for an LCD, we listed all the multiples and then found the one that was in the both lists, the smallest one. Here we're hunting for the biggest one that's in both lists. Now, the only justification for doing the multiples was to avoid primes. And so certainly this is a way of finding a GCF, but I would encourage you much more to do primes because it's so powerful. But I didn't do what was thorough enough in terms of the problems, because I had several of you tell me that as you tried looking at the problems on the computerized homework, this one caused you some frustration at the time you were looking at it. So my due diligence was not quite what it should have been in this section. Is there further question about the process here? Okay, that was a critique, not a question. But if I can paraphrase it, you did not like it. But you love the primes, right? No, come on, you can't not like both. You have to like one of them. This whole section, but it likes you. Okay, and you will learn to like it. Because if something likes you, then you're supposed to reciprocate. Probably won't buy that, but any other questions in this section?
This is the 3.5, correct?
3.5, yes.
Okay.
Okay.
I just want to know, like, if I was doing the problem, like, so I went over a few at home yesterday, and I just want to know.
Okay. You have one there that you can share with me? Okay, let's go to the board again, Chris. What is the problem, Dion? Or do you need some time to find it?
Yes.
Okay, need some time to find it. Kim? Not yet. I'm just restricting myself to 3.5. James?
Oh, yeah, matter of fact, James had it the other day. He asked you to put on the board, the one with the 6. It had the one he asked you to put on the board, yeah, I believe it was the most hardest one, yeah.
Okay, the one in which we had a binomial times a trinomial?
Yeah. Yeah, the 6y something.
No, not yet. Okay, you had a different one first. Let's go back to that one, and then I'll come back to Dion's question. I know what's involved there. Got a landscaper doing something, and the landscaper's planting what?
A sprinkler system that will require preset PVC pipe to be connected in place in the ground. The trenches he will dig or to be
Okay, let me write down some numbers here. 40 feet and what number? 32 feet, you said? 32 feet and 24 feet in length. So we're laying a sprinkler system, PVC pipe perhaps. And what is the question asking you to do? Okay, so you're loading the truck. Your equipment for cutting this is at the shop, and you don't carry a cutter with you, although anybody laying PVC would. But let's say that it's brass pipe or something, and you just would like to have some nice cuts, and you're going to do this with fittings that you have, so none of this glue. You want this to last for at least forever. So you're going to go ahead and try to get modulars. So you want the largest length of pipe that you can just take it out of the truck and know you're going to be able to do it. Now, as you look at this, an 8 will do it. From the standpoint, 5/8 will give me the 40, 4/8 will give me the 32, and 3/8 will give me the 24. So 8, just by thinking of the numbers, is your GCF. And the only thing that's an arguable point here is joining that pipe usually involves what? Some additional space. So because if I join it, even if it's PVC, you have a coupler and it doesn't come flush. So you might pick up a 1/4 inch in each one. So you're still a little bit at risk. Where 40 feet, no problem. And if you've ever laid PVC, better not to have any cuts. Give me a length 40 feet long, no leakage until the tree roots get into it and all those things. What would be the technique you use? Well, you could do the one we just talked about. That is, you look at the 40 and you say, okay, 1, and then a 2, and then a 4, and then an 8, and then a 10, and then a 20, and I believe then you get up to the 40, and then that's it, right? Did I miss the 5? I did indeed. Thank you. Missed the 5. So I have 1, 2, 4, and 5. Thank you. Did I miss anything else? Okay, the 32 I'm going to have what? The 1, the 2, the 4, the 8, the 16, and 32. And then the 24 is my 1, 2, 3, 4, 6, 8, 12, 24. So that's one technique, and this is the one that's being referenced as we go back to the document camp. We're waiting. I've got a nice, there we go. Now, what is the largest number? And I can't do the nice little slant thing like the 12. Let's come back to the board now. So I'm going to just circle the 8s and say, okay, that is the largest number I have in common to all 3 lists. That would be one approach. Now, what's the other approach? If we're going to use primes, you would say that 40, so I'm just going to come up here now and do the 40 as a product of primes. So that's 2 to the 3rd, 5 to the 1st, correct? The 32 is going to be 2 to the 5th. And the 24 is going to be 2 to the 3rd, 3 to the 1st. So what is the only prime common to all lists? The 2. And what is its lowest exponent? Not its highest. The 3. There's my 8. This way? Okay, I made the sale, right? This is longer, this is faster, and you aren't quite as inclined to do what I did here where I missed one of them. Okay? But both techniques. Does that answer your question, James? Now, once you know what you're doing in this problem, then it's pretty straightforward. If you don't quite understand the intent of the problem, and this is a very similar problem to when I did multiples and I was talking about going down to the transportation center where you have buses, that are going in the same, well, they have different routes, but they all come back at some time later where all 3 buses are there at the same time. And so we talked about the least common multiple. Well, here's now the greatest common divisor, greatest common factor, done in much the same way. What was not clear, I think, is that you're trying to get these modular pieces so you don't have to do any cutting. And if you understand that all you're hunting for is the GCF or the GCD, it's a very direct problem. The difficulty is to make that judgment when you just read the English. I agree. Now, Dion, coming back to the question about a binomial times a trinomial.
Yeah, can we just make one up?
I'd be happy to. Let's try just making one up. My choice. Thank you. With malice aforethought. Okay, x plus 1 times x squared minus x plus 1. That's not craziness. That's a good problem. Okay, I'm headed for something. Let me walk away from there for a moment because that little piece of chalk up on the desk is not going to get me through the hour. Okay. This result is going to be rather nice, what I'm going to illustrate here. And this is one of those problems where it gets better the longer you work at it. So here goes. You have choices. The choice is to take this out front and multiply it by each of these. And that's what we talked about yesterday. And then the other alternative is to do what? Take this first part here and multiply everything by that x, then come back and multiply 1 times it all. Both work. From an efficiency point of view, I sort of like taking the x times everything. So I'll do that the first step. And again, Isaac, what would you suggest I write in there that's missing? Very good. The 1. Okay, you used it. Very good. Now, that's x to the third because x to the first times x to the second, I add the exponents. That's why we put that 1 there. Then x times minus x is minus x squared because technically that's x to the first, and I would suggest you put that one in. Then x to the first times the 1 is just x, and I'll leave the exponent there just to be safe. Now, I take the 1 and multiply it by each of these 3. Now, that technically is just x squared. I don't know if you would like to put a plus there just to remind yourself that it's positive. And then the 1 times the negative x would be just negative x to the first, and then plus 1. Anybody see something? No, I'm not cross-canceling. I'm going to be adding, and I have inverses, correct? But addition inverses, the inverse for addition. These two are going to go to 0. These two are going to go to 0. And this whole thing just becomes x cubed plus 1. That's neat.
I think that was more difficult for me because it's just x. I got to be able to really look at the problem instead of it actually having numbers instead of...
Yeah, if you had an x to the third out here, then you wouldn't be inclined to forget that's x to the first, because what we did yesterday as we looked at this, without the 1, we tended to see just x squared.
Exactly, that's why.
Okay, but then put the 1 in. Now, this happens to be in the same category of arithmetic where I tell you that 35 can be written as 5 times 7. Otherwise, you took 5 times 7 and got 35, so if you start here, you can write these factors, correct? So if I give you this, you now know, if you memorize that, that is x plus 1 times x squared minus x plus 1. And you have factored a third-degree binomial into the product of a binomial times a trinomial. And if you were to be in a Math 70 today instead of a 20, I'd say, okay, memorize that for the next 15 weeks. That particular problem. Because we would generalize it. And that would be a problem. I mean, this is a very common problem for me on an algebra test. Start here, and I want this factoring. Okay? Dion.
I found it easy because, like how you put on the board yesterday, I was writing this stuff down. I was practicing while you was talking. How you had the numbers, and I would use the arrows.
Yes.
The number that was closest to the outside.
Like the x.
The open parentheses. Oh, the FOIL. That's what you call it. I'm
No, this would not be the FOIL here, but what you're referring to, I made this comment. If I have A times B plus C plus D, then I said we distribute those arrows, and we did a lot of that. So in a sense, if I now have, instead of that, A plus B times C plus D plus E, then what I'm doing, watch the arrows. If those chase you at night in your sleep, then you understand what's happened. But that's the technique I'm using at the moment. Now, what's your alternative? I could have said x plus 1 times x squared. Then minus x plus 1 times x. Then plus x plus 1 times 1, where I'm taking this whole expression here and distributing it over the trinomial. That's an alternative. Your choice.
I thought you wasn't taking. Cause I remember the other problem yesterday, or I believe it was yesterday, where you took or it was a 6. I think it was a 6A, and then you went underneath. You went underneath. Your arrows went from.
Well, I have like this is underneath.
Not that one, though, but it wasn't that. It was the A going to the C, and then to the D. You know what I mean? That's where you get started. Like.
Yeah, I did that.
No. From the bottom though.
I went here.
It's the same thing though.
Yes, whether I do in top or bottom, whether I'm above the water, below the water, it comes out the same. Just looks different. My apologies if I reversed it. Okay.
Not because if it was numbers, it would have been different, right?
No.
No?
If I put my arrows below or put the arrows above, I'm still distributing it over the 3.
It's like say if 9 represented A,
yes.
Like 7 represented B, right? And you were trying to, it would be different because you're multiplying the
9 times the 7, or the 9 by the 7 still.
No.
Okay, we're going to have to look at that differently because at the moment I would need to look at another problem, and I need to cover 3-6. So I'm going to let go of this and go on to 3-6 and make sure I've done that. So I'm going to come back center, Chris, just so you know where I'm coming, or going, whatever. And before we do that, Jennifer, do you have the Fibonacci problem with you?
Oh, no, I can get it.
Get it, please. Please, if you would. We're going to take a moment for a digression. This was courtesy of Colt. Going to the document cam, Raylene's son, found a pine cone for me. Okay, and what do we find in pine cones? Fibonacci numbers. Now, this was coincidental because Raylene brought this to me, and then Jennifer brought me something from the paper. But do you see these spirals right here? And then the spirals going this way? And what was our argument about the spirals? Thank you. Appreciate that. What was the argument about those spirals? If you count the spirals, whether you do it on this pine cone or a pineapple, the number of spirals going one way versus the other way will, in both cases, be a what? A Fibonacci number. That's the nice part about it. Now, what we typically do, let's come off there for a moment. I don't know if I can pull this off, but we'll try it. Because the reason I say that, this has, I think, been in the water at some point as we come back to here, and it's awfully hard to see them. But coming off there again, if I had it under a sun lamp for a little bit longer. Okay, where are we going to start, Carl? What I'm trying to do, yeah, not so good when you're trying to do this and it suddenly changes on you. I'll try to show this much. Now, what I've done is try to take these spirals, and I've tried, this is on a spiral here, so I count what we call the bracts here. So there's 1 starting here, then 2, 3, and so on. And then notice how this is going this way. Eventually they come around in the back and meet. And so if you count the number on each, you'll find Fibonacci numbers again. So just a reminder of that, if you're out pine cone hunting, let's come off there. There was a neat problem. I wouldn't say problem. It could be a problem. I love this. This is Foxtrot on Sunday. Okay, 1 cheesy tortilla chip. And he says, 1 cheesy tortilla chip. 2 cheesy tortilla chips. 3 cheesy tortilla chips. 1, 1, 2, 3. 5 cheesy tortilla chips. 8 cheesy tortilla chips. Do you recognize the pattern? 1, 1, 2, 3, 5, 8. Math geeks shouldn't be allowed anywhere near certain foods. The question she asked, what's wrong with the Fibonacci nachos? And he responds, there are only 12 left. Now what? Because what's the next Fibonacci number? 13. Yes! You got to love this. Okay, thank you, Chris. Okay, now, if you had no mathematics, if you hadn't taken Math 10, you would not have appreciated that. Sandra, you still don't. I can tell from the look in your face. Okay, James. Yes. Yes, this was the rabbit problem that Leonardo da Pisa wrote about in Liber Abaci. Yes. Sandra.
So what happened with that, like that theory that we did on a Friday tutorial where they were trying to figure out, I don't know, something, and you found like a reversed way to it, like, tell us all about the Fibonacci and if you use prime numbers or something.
Oh, yeah.
Sandra's remembering something about a tutorial we did earlier about Fibonacci numbers, and we found something on the internet, and at the moment I'm not having the recall that Isaac said, oh yeah, you two get together and you tell me about it maybe some other day, and we'll come back to the Fibonaccis.
The Fibonacci.
Yes, the Fibonaccios. The Fibonacci numbers. That's good. Thank you, Jennifer. I like that. So that was our moment of a diversion. I think it's great in Foxtrot because they do a lot of mathematics. Good stuff. Okay, we talked about this yesterday. I'll just put it back up on the screen. And you know my critique. Nobody else I've seen does it this way. N to the A divided by N to the B is N to the A minus B. Everybody else says A to the M over A to the N is A to the M minus N. So I guess everybody has a right to write their book the way they want.
It's a lot of N.
So in this case, just want to remind you that as I go to the board on this, I come over here, and I didn't telegraph that very well. I'm sorry, Chris. But if I come here, typically, if you look at an algebra book, and that's my concern, this statement is going to be written this way. Then you are going to subtract the exponents. Now, there is usually one little caveat here, one little restriction that we make, and that for now, the M must be larger than the N so that I get a positive exponent. We will extend this so that M could be smaller than N, and when you subtract, get a negative exponent. Remember, we've done this, just to remind you.
Just like the line.
When I talked about 10 to the minus 3 being 1 over 10 to the third, that we said with expanded notation, with decimals, we said that if you have 1 over 10 to the third, it's the same as 10 to the minus third, so you know at least what a negative exponent means. So if I said in this problem here that, for example, if M was 5, I'll rephrase that. If M is 2, so let's do something like this. If I had a to the second over a to the fifth, and I were to subtract, I'd have a to the minus 3, correct? And that would be the same as 1 over a cubed. One more time, same argument that we had here. 10 to the minus 3 is understood to mean 1 over 10 to the third. So if I look at this and do the subtraction, this comes out a to the negative 3. But if I just cancel, I'll end up with 1 over a to the third. And so it's exactly the same argument we had with 10, even though my base is different. And if I'm again blocking, make sure you're looking at the television. Yes?
So
Michael.
You have a negative going to end up with a fraction.
Okay, it's a good way of thinking of it. Michael said if you have an exponent that's negative, you would end up ultimately with a fraction. Yes. Technically, it's reciprocal in the sense that if you had a to the minus 3, you get 1 over a to the third. So it's not technically a reciprocal. I said that badly. Same concept, though, in some way. Okay, back to the document count. So for most part, you're going to find authors in algebra books at this point saying, just what we're doing here, make sure that when you write the answer, you have a positive exponent. And it's interesting here that there's nothing in this problem, the way it's stated that I can see, in which there's a restriction. So I don't know if we're headed for negative exponents or not. We do note that the base cannot be 0. So in this problem, coming back to it one more time, Chris, n cannot equal 0 because you can't divide by 0. So coming off there. I made the comment to you in the counting unit in Math 10 that any number to the 0 power other than 0 is 1. Let's look at the bottom of 207. Here's my problem. I'll bring that down just a little bit. Note that if you, on this side, right here, went ahead and canceled, you just have a 1, correct? But if you subtract the exponents, you're getting 2 to the 0. Now, whether I have a 2 here, a 4, a 5, any base, as long as it's the same, I'll get that base to the 0 power, and it'll always reduce on the left side to 1. You couldn't have 0 over 0. So we argue then that any value other than 0 to the 0 power is 1. So if I wanted to make a statement similar to what I've done on the board, and I'm going to go back, Chris, to that same thing. I have a little bit of space over here on the right side. I could just argue that a to the 0 is 1, a not equal to 0. So that's generalizing that statement. Okay, Michael, question.
Well, since 2 to the third over 2 to the third, wouldn't that...
Okay, let me come back to the document cam. The comment is, if I take 2 to the third over 2 to the third, wouldn't that just be a 1? It is, indeed. But what happens if I just use the rule that we just talked about, subtract the exponents? So the base is 2 in each case. Subtract the exponent down here in the denominator from the exponent in the numerator, and you get 3 minus 3, which is 2 to the 0. Hence, coming off there, my definition is that any base I want, other than 0, to the 0 power would equal 1 for exactly what you observed. So I make that definition. And it allows me to subtract exponents and have consistency. So we used it in the sense that when we were in base 2, we said we started with 2 to the 0, went 2 to the first, 2 to the second, 2 to the third for our place values. And 2 to the 0 was 1. And you had a choice to write 2 to the 0 or a 1 when you did expanded notation. And I'm hoping those pieces go together a little bit for you. Now, I also yesterday showed you a trinomial where I had some common factors. And I'd like to go to the sideboard to talk about that, and I'll just create one for the moment. But before I do that, let me see if I can find something of a similar nature in your book and uncluttered. There's two ways of doing this, and I'm going to look at this problem on page 210. See if I can get that down and in focus and flattened out. I need a big rock is what I need. Stapler will do. Okay, let's cut to that. Now forget about the denominator for a moment. Just focusing on the numerator. And I'm going to go over here to the side and write this out. So I have 24x to the 9th. And I have a minus 20x to the 7th. And I have a plus 4x to the 6th. Now, technically at this point, it is divided by 4x to the 6th. But if I were just to give you this problem in a test environment, I might ask you to simply, starting with this trinomial, tell me the greatest common factor, independent of the 4x to the 6th. So you would ask, what is the variable that's in common to every term? It's x, the variable, not the numerical value. I take the lowest exponent, which is a 6. Then I ask, and this is where you could technically write the list of all the divisors of 24, 20, and 4, or you can take prime factoring for all of them, or you can look up into the ceiling like what's that number, and then come back and say, oh, 4. Now, it's a dead giveaway because 4 is the only thing that will divide here, and then you ask, will it divide each of these? Yes. So the 4x to the 6th is your GCF. Now, that's one level. Now, the other level is to take something like 4x to the 6th and divide it into here. So I could say I have this trinomial with the divide symbol over here and then a 4x to the 6th. Or I can do this, and I made a comment to you yesterday that I can look at A plus B plus C over D, because that's what I'm looking at. And I know that that is A over D plus B over D plus C over D. We usually go from here to here. But here's a case where I want to reverse it. So this becomes 24x to the 9th over 4x to the 6th. Then I have a 20x to the 7th over 4x to the 6th. Then I have the 4x to the 6th over 4x to the 6th. The 4 into the 24 giving you 6. And then the question, do you take time to do this? Or do you just say, I can see that's 6x to the 3rd? For a while, if you're not feeling real comfortable about the subtraction of the exponents, I think it helps to do this. But at some point, you've got to give that up and just quickly go to your answer. The minus sign here has to be brought across. I have 4 into 20 going for a 5. Then x to the 7 minus 6, so I have minus 5x. I hope you realize this is technically 1 times x to the 6 minus 6, and I'm doing that, Michael, just to respond again, that is 1 times x to the 0, but we usually just say 1, because you had the same numerator as you did denominator, so it would not be uncommon just to leave off this, and so I have a 3rd degree trinomial. I want you to at least be aware that there's another way of doing this problem. Which seems perhaps familiar. It depends on how you liked long division. So you take 4x to the 6th into here. And it goes what? 5x to the 3rd, correct? 6 would be a better answer. Thank you. How I made that a 25 and a 5, I have no idea. But 4 into 20, I guess it would, but it was 24. So 6x to the 3rd. Now, you could do what? 24x to the 9th. Subtract and bring down your next term. Reminiscent of long division. And then I would say 4x to the 6th goes into here. Now I get my 5, okay? And I have x to the 1st. And I could write down negative 20x to the 7th and subtract and then bring down what? The 4x to the 6th. And then say plus 1, and without dropping any further, I would put down there. Now, that's not really necessary at this point, but if I can get you to buy this, then I've got to stop and think what problem I did. I could do a problem like that. Okay, and that's called a long division of a binomial into, in a sense, a polynomial, and I had to do what? Hold space, just like when you had a number, let's say you had 15 going into 1, 0, 0, 1. Something like that. You had placeholders, right? It's the same idea. Now, I don't want to carry this through because that's beyond the scope of where I am today. But I want you to realize what I did here as we slide over for a minute, Chris. Slide over to here. That process, and we don't need to change what we have up here, would be a same thing. No, I didn't need to go there. Back up just to here for me for a moment, just to the edge there. Keep going. Keep going. Thing. So I'm going to do this kind of thing with that, and I'll leave it there for the moment. Let's just leave that on the screen the way it is. Question, Michael, before I leave that? Where did I get what from? This part up here? Ah, camera 1, Chris, below the below the clock, where I have x plus 1 as a binomial times the trinomial x squared minus x plus 1 with all the little arrows going all over the place near the center of the board. You got it? I want this sometime there, okay? Now, if I know this binomial times that trinomial gives this answer, shouldn't I be able to divide x plus 1 into this and get that? If I know 5 times 7 is 35, I could divide 5 into 35 and I should get 7. Let's leave this here for a moment. I'm beginning to regret I did this, but I've come back to here now. Okay, now we'll slide over. This was x cubed plus 1. The thing that disguised it, I had to have placeholders for when I do the division. So if I had an x to the cubed, I'd have to have an x squared and an x to the first and stair step down. So the point being, I'll just write what the answer with this has to be. It has to be x squared minus x plus 1 when I get done. Because when I multiplied x plus 1 times this, I got x cubed plus 1. That's how you check a division problem. I haven't told you how to do it, and I'm not. I've buried myself far enough here. All I want you to understand again is that we are going to go to divisions like this. And it's going to look, as we now slide over, very much like what I did here. Keep going, I need the division there. Okay, which was, as we slide over a little bit more, just another way of doing what I had here. I'm going to leave that. And if it's uncomfortable a little bit, that's okay. You know, I understand what you like and why. But that is, in essence, what's done in your text. As we look now at the document cam, and I have here the 3 parts that we just had on the board with exactly the same result. And notice the only thing that I sort of would like to have seen is that this became x to the 0, hence a 1. And that's not quite as clear there as it might be. Okay, let's look at a phrase. There are a couple problems here. I have to be a little bit careful that I cover everything because I made the error of not covering quite in the depth I should have. Now, to do this problem, Chris, I need to come back. No, hold on. What I want to do is take camera 2. And I want camera 2 to come back over to here. Okay, so I'll show you where I am there. I want camera 2 back over there for a moment, because this is a problem we had in our review tests in Math 10. I give you a product and I give you one of the factors. Okay, so as I come back to there, it's called the missing factor. Okay, the missing factor in this kind of problem is that if 35 is equal to 5 times 7, and I know that, I can sometimes write this in this way. 35 equals something times 7. So I tell you one of the factors, I tell you the product, and then you have to do what? Divide to get the other factor. That's very similar to a problem in one of the review tests we had in Math 10. Now let's come back to the book and the document cam. And there we see that we have a product of 24x to the 5th. One of the factors is 6x cubed. You want to find the other one. Well, the one way of doing it is just divide 6x to the 3rd into what? 24x to the 5th. And is it reasonable to say that you can see 4x squared without pushing it? Or you could put the 24x to the 5th over the 6x cubed. And that's exactly what's done here in the solution. Okay, so it's a fairly typical problem. And how do you verify you're right? You multiply it back out, and that's what's done in the next step. So as we come off there for a moment, let's look at this binomial. This is again on page 211 as we go to the document cam. One way of doing this is to divide the 3 into each part, correct? Or you can ask, what binomial would I need with the distributive property that when I multiply the 3 times both pieces, I would get 6x and a 15? Well, one way of doing that problem is to do the division. Okay? And you may be able to do that without the division. The very bottom of the page is another objective, which is factoring the GCF out of a polynomial. Now that actor means factor, the GCF out of a polynomial. So as I now bring camera 2 back to the other side, Chris, all the way over to the far left of the side board, where I had 4x to the 6th in the denominator. Okay. So I have a 24x to the 9th, if you'll bring that into the camera now. Now that is what is going to be talked about here in the sense that I want to factor out that GCF. When we said the GCF was 4x to the 6th. So if I'm going to factor that out as I go to the side board, and I'll just leave that up there for a moment, then what I would do, okay, so I have determined that if I were to take this 4x to the 6th out, I would have what? This trinomial. So I can rewrite this entire problem and say, as we slide back, that if I factor out the 4x to the 6th, I have what's left, which we found was 6x to the 3rd minus 5x plus 1. And so we have factored that original trinomial by factoring out the GCF. And that's something we'd like to do. Okay? Let me explain why. Let's slide over now a little bit here. Nice pan, that looks good. Yeah, I've got to remember what we've done. We've said something like this, that x plus 2 times x minus 2, there was a shortcut for that, did we not? We have a binomial times a binomial. We call this what compared to here? the conjugate, right? And we had a discussion. Marisol and Sandra and I had a discussion. What made this was a conjugate. These two numbers are the same. Two parts are the same, I should say. And we had a plus here and a minus here. Hence, a conjugate, a binomial and its conjugate. What was the quick answer? What? Yeah, I heard the minus 4. That was right. I just didn't.
No, x squared.
X squared minus 4. Yes. Okay. I would suggest maybe reviewing that. Okay, now, if I gave you this, remember my comment was that we could go backwards and we get these are the factors of this binomial.
If you requested for its conjugate.
No, if I said, I'm giving you this difference of two
So
terms,
how did you write it out? Because, see, I'd be
this is the answer. So starting here, you write x plus 2 times x minus 2, noting that this is x to the second minus 2 to the second. The difference of two squares. That's the key. Now, again, I don't want to get buried going any further. We did this problem. Leave it at that for the moment. Now, I want you to consider this just to understand where we're headed. If I gave you 3x to the fifth minus 12x to the third, what is the GCF? I have not heard a correct answer yet. 3x to the third?
Yes.
X is in common to both.
Right.
Take the lowest exponent, hence x cubed. The 3 is in common to both, so that, now, if I factor out the 3x cubed, what will I have left? X squared minus 4. Do you agree? Then I note that I could write this as a binomial times its conjugate, and we call that factoring. So we have to learn how to take out the GCF, and then with the goal, ultimately, of breaking it into a product of prime terms, not prime numbers. Prime terms means there's nothing I can do to break the x plus 2 and the x minus 2 further. So we are trying to write a polynomial as a product of factors, and each factor cannot be made in any smaller way. So it's sort of prime that way. Leaving that on the board. What you have to understand is that the things we are doing here as we come back center, the things that we are doing here are very, very much a matter of having to do something in the future. Every step we do is that way. And so as you look at what I have on the next part, and this is a procedure, and I'm just going to show that, and then I'm going to have to take a moment to answer a question, so I'll go off camera. But let's look at this. A polynomial is equal to, and again I need to flatten this out in some way. That's fairly reasonable. So the polynomial is the GCF times the polynomial over the GCF. That's what we've been doing. And I'm going to cut the microphone for a moment. Delay there momentarily. That GCF times the polynomial of the GCF is precisely what we've been doing. Let's come back center. that is basically everything in the section except for a bunch of problems. And I'm going to try, no, I just come back to me in center. I'd like to go ahead and ask, of course, that you do the assignment in 3-6, and I realize that since tomorrow the college is closed, Monday the college is closed, and getting an opportunity to work in the computer between now and then, if you don't have access to a computer, is going to be difficult. You have two choices now. Since you have 4 days, I think spending 4 days doing nothing because of not having a computer would be dangerous. You could print out off of the web page, and I don't know if I can show that in a minute. I'll give it a shot and see if it comes up quickly. Yes, it is. This may be better than I thought. What I'm going to do is come to the spring schedule, and I'm going to come down to week 5, which is where we are, and I'm going to slide down there and try to get what I wanted. This is the assignment on 3-6, and that is, yes, 3-6. And if we look down there, they're the homework problems. My point is those are on the computer, and you go to any lab and get that printed out and at least spend time on those problems on the weekend. I will run I'll allow you to work on 3-5 and 3-6 through the weekend coming up to the 17th, and I'll make sure I have that done. So, Chris, we are out of time.